Okay, in this video I'm going to begin section 7.2. In 7.1 we were just kind of talking about the basics of the normal distribution, just some of the properties, what it means to be normally distributed. It means that the data is coming, creating a histogram where the shape of the histogram is bell-shaped and symmetric. Another big idea that we took away from section 7.1 is that changing the variable from x to z does no harm, because the area that is between two x values will be the same area, the exact same area as the area that is between two z values. Okay, now the whole idea with changing the variable is so that we can be able to use a table in order to then be able to get a probability. Okay, so in this section we're going to be using the standard normal table to answer some problems, and I'll show you how to use that table here in just a moment. 7.2 has quite a bit of information in it, so this will likely be split up into a few videos here. All right, so let's take a look at problem 6. Now they want us to determine the area under the standard normal curve. Remember, the standard normal curve just means that you have switched the variable from x to z. Okay, and so we want to find the area under the standard normal curve that lies to the left of z equals 1.68, and then we'll interpret that as a probability. All right, to find probabilities for a normal random variable, we use a table. This table right here, this is in your book, and I'll show you how to use this for the upcoming problems. We use a table. Now the table will always give you the area under the standard normal curve, which is why we have to find a z-score, but it's going to be the area under the standard normal curve that is to the left of a specific z-score. Okay, so let's go back to this problem here. Remember, with the standard normal distribution, the mean is always 0 and the standard deviation is always 1. Okay, the mean is always in the center. So I want to label the center mu equals 0, and now the z-score that is given to me here is bigger than the mean. So I want to position that number just to the right of the center, and we would like to find the area that is to the left of 1.68. So I'm going to shade the area that is to the left there, and that shaded area is what I'd like to find. So now I'm going to go to the table and look up my answer. On this table we have z-scores that we're going to have to match up in order to calculate our probability. In using the table, you are going to omit the rightmost digit in the number. So for this problem, I'm going to omit the 8, and I'm going to scan down the leftmost column until I find 1.6, and I'm going to match that with the column over here that is for 0.08, since 8 was the rightmost digit in that number that I had. Okay, so if I match up the row that is for 1.6 and the column that is for 0.08, I'm getting 0.9535. So that number, 0.9535, would be my answer. Okay, that's the shaded region that we see underneath the bell curve. Now, remember that area and probability mean the same thing. So one way that I can interpret this is as an area, right? The area of the shaded region is 0.9535, but I can also look at this as a probability question. Okay, the probability of z being less than 1.68 means that I'm describing the area to the left of 1.68, and that area, we went to the table and looked it up, it's 0.9535. Okay, now there is no formula that we'll be using to calculate our probabilities like you saw in the last chapter where we looked at the binomial probability formula. There is a formula, okay, but you guys are not using some rigorous formula. It involves heavy calculus, and what somebody has done for us is they've used that formula to calculate areas under the bell curve. They've looked at really every situation that you'd ever care about underneath underneath the bell curve, and they've created this table for us, which makes life way easier than what it could have been, because now we just simply go to the table and look up our answer. Let's take a look at problem 7. In problem 7, we want to determine the area under the standard normal curve that is to the right of negative 0.46. And we're going to interpret that as a probability. Okay, so I'm working with the standard normal curve again. Here's the z-axis. I've got all these z values. The mean is always 0, going to go right in the center. Now the z-score that is given here is less than the mean. Right? Negative 0.46 is less than 0, so I need to position that to the left of the center. And we would like to know the area that is to the right of negative 0.46. So I'll be shading the area that is to the right, and that shaded area is what I'd like to find in the problem. Okay, now the table only gives area to the left of the z-score. In this problem, I'd like to know the area to the right of the z-score. The area under the entire curve is 1, right? The normal density curve is a probability density function. That's just fancy words for saying that the total area underneath the curve would be 1. Okay, so think about it as you're representing all 100% of the data underneath this bell curve here. And of course, you can't have a probability greater than 1 too, right? So that would make sense why we would want that to be a 1 as the max value there. So if I were to find the area to the left of negative 0.46 using the table, and then subtract that number from 1, I'll be able to get the area that would be to the right of that z-score. Okay, so I'll be using the complement rule. In general, to find the area to the right of a z-score, you're going to take 1 minus the area to the left of the z-score. All right, let's go to the table. And I'm looking for the area to the left of negative 0.46. So in the chart, I want to scan down this column here until I see negative 0.4. Here it is. And I'm going to match that with the column that is for 0.06, since 6 was the last digit. And that number that I see is 0.3228. So 0.3228 would be the unshaded area that is to the left of negative 0.46. If I subtract that number from 1, 0.6772 would be the area that is to the right of the z-score. So 0.6772 would be my answer. Now again, I can look at this as a probability question. When I write the probability that z greater than negative 0.46, what that means is that I'm describing the area to the right of that z-score, which is what we want in the problem. Whenever the sign is facing away from z, you're talking about area to the left. Whenever it's facing towards z, you're talking about area to the right. So, of course, you want to make sure that you have the sign facing in the correct direction there, depending on what you're talking about, area to the left or area to the right. Now, in this problem, we had to use the complement rule, right? So, 1 minus the probability of the opposite of z being greater than negative 0.46 is for z to be less than negative 0.46. Now, you want to switch the sign here like I've done because you're now describing area to the left, right? The area to the right of a z-score is 1 minus the area to the left of the z-score. Table only gives the area to the left, so we went to the table. We looked up that number that is to the left of negative 0.46, and we subtract that from 1, and we get our answer. Okay, so the probability of being greater than negative 0.46 is also 0.6772. Area and probability mean the same thing. One thing that I want you guys to notice here is z-scores are always going to be rounded to 2-digit decimals, and areas and probabilities are always going to be rounded to 4-digit decimals. Don't get those numbers mixed up. Some students will do that, and that will lead to confusion down the road when you mix up z-scores and probabilities. Z-scores are totally different from probabilities, right? A probability can't be bigger than 1. Also, a probability can't be negative. Okay? The z-scores are always the 2-digit decimals that are going to go on the horizontal axis. The areas or probabilities, same thing, are always the 4-digit decimals that are going to go underneath the bell curve. Again, don't mix those up. Here's another problem. Okay, problem 8. We want to determine the area under the standard normal curve that lies between negative 1.35 and 2.01. Okay, so again, I've already got a bell curve drawn here, and I've labeled the z-axis. The mean is at 0 right in the center, and the first z-score is less than the mean, so I'll go ahead and mark that about right here at negative 1.35. And then my other z-score is bigger than the mean. It's also more distant from the mean than the first number was. And so I've marked 2.01 about right here. Now I need to find the area between these two z-scores, so I've shaded that area, and that shaded area is what I'd like to know. Again, the table only gives you area to the left of a z-score. Now here we need the area between two z-scores. The plan is going to be to find the area that is to the left of the bigger z-score. And now we don't want that whole area, right? We want to subtract the unwanted space. So we're going to subtract the area that is to the left of the smaller z-score. In general, that's going to be the plan for when you want to find the area between two z-scores. Take the area to the left of the bigger z-score minus the area to the left of the smaller z-score. Well, let's go ahead and look up our areas now. So the area to the left of 2.01, okay, so here's 2.0 right there, and then match that up with the column that is for 0.01, and I'm getting 0.9778. So the area to the left of 2.01 is 0.9778, and I want to subtract the area to the left of negative 1.35. Again, I'll go to the table, and negative 1.35, the area to the left is 0.0885. Okay, and that's what I got here. Subtract those two numbers, and so that shaded area is 0.8893. Now again, this is a probability question also, right? So using the probability notation, here's how I'd write this down. The probability that z is between negative 1.35 and 2.01 would be written this way. Now, the plan is to find the area to the left of the larger z-score minus the area to the left of the smaller z-score. The probability that z less than 2.001 means you're talking about the area to the left of 2.01. The probability that z less than negative 1.35 means that you're talking about the area to the left of negative 1.35. Both of these are less than signs. That's what I want, since both of them are describing area to the left. We then went to the chart and looked up those two areas and then subtracted the numbers in order to get 0.8893. Okay. Here's another comment which I've already mentioned. Make sure that you know the difference between a z-score and a probability. That is the mistake that I see students will make in this topic, is they'll get those numbers confused, and that will be a big problem going forward if you can't keep those numbers separate. Okay. A couple of other things I want to mention here. Now, first, there are many different ways that your book can ask you essentially the same question. Okay. One way that they can ask you the question here is they can give it as a worded question, like what I'm doing here, in these problems. They might, they'll say, determine the area under the standard normal curve that lies between negative 1.35 and 2.01. We've done that. Okay. Another way that they can ask the same thing is they can give you a picture. They might already have a picture drawn of the bell curve, and the z-score is labeled there, and they'll say, find the area of the shaded region. Well, that's the same question. Right, we've found that area. It's 0.8893. Another way that they can ask the same thing is as a probability question. Okay, they could say, find the probability that negative 1.35 less than z less than 2.01. We've done that, right? That probability and area are the same thing. So with a continuous random variable, and we found that probability is 0.8893. All those questions are the same thing. It's just how they're asking it. Okay. Another thing I wanted to mention here. So when you're This would be more important in class if we were drawing bell curves and stuff and labeling. But it's not an exact science for where you're positioning z-scores, but I do see students position these numbers in spots that wouldn't be correct, okay? Like in this problem here, I wouldn't want negative 1.35 to be like right just to the left of this vertical axis. That would be poor positioning. I also wouldn't want negative 1.35 to be way out here. That would be poor positioning. The reason is because, so on this chart, the smallest z-score that is given is negative 3.49. The biggest z-score that is given is 3.49. Okay, now the probabilities are going to increase here from roughly 0 to roughly 1. Right? Probability can't be outside of 0 and 1. So on a picture, you got to figure that on the tail ends here, you're going to be at, here's like negative 3.49, and here would be 3.49. So if I'm positioning negative 1.35 right here, let's say, that would be poor positioning if negative 3.49 is way out here. Also, I wouldn't want to position negative 1.35 like way out here if negative 3.49 should be way out here. Okay, now again, it's not an exact science, okay, but the labeling would be important, you know, if, like I said, if you were drawing this by hand in class. There's another note below. It says, for a continuous random variable, the probability of observing a specific value of the random variable is 0. Notice how in these problems, I am using less than signs or greater than signs. Okay, that is a necessary thing in the notation. I wouldn't want to just say probability of 2.01. That would be 0. Okay, the reason is because if you only write probability of 2.01, you're talking about a vertical line which has no area. So that number would be 0, and if done correctly, you would get a wrong answer. Okay, we need the less than. We need the z less than or z greater than, whichever is appropriate for the problem. Okay. Also, equal signs don't matter in the event of a continuous random variable. So, like if I had an equal sign right here, you know, if this were a less than or equal to, that wouldn't affect anything. I would still get the exact same answer as you see here because my procedure is going to be exactly the same, right? I'm still going to go to the chart and look up the area that is to the left of 2.01, and it's going to be that same number, 0.9778. Okay? Equal signs don't matter if they're in the event of a normal random variable, okay? Because it's all about area to the left. Now, careful about that because equal signs definitely matter if you're talking about a binomial random variable, right? That's a totally different variable, okay? It's different here because we're just simply going to the chart and looking up the area to the left. It doesn't matter if we're including that start point or not. It's all about area to the left. All right, I'm going to stop the video right here.